One of the key ideas and motivations for learning real analysis is literally to invent new numbers and, more importantly, new functions. Now, let me explain what I mean by that. There was a problem around 17th or 18th century that many mathematicians, including Bernoulli, was thinking about. And it's a problem related to compound interest formula. And the formula is like this, and if you, this you can find in any arithmetic book, that the after t years, so if t is the number of years of compounding, if p is the principal amount that you deposited in the bank, then you have this formula where r is the rate of interest, and n is the number of times compounded. So maybe you are compounding twice every year, or maybe you are compounding 3 times every year, and so on. P is the principal, by the way. So this was a formula that was well known by bankers for a long amount of time. Now, mathematicians wanted to take this particular formula to its extreme. So what they did is they started by setting up p equals to 1. So maybe you can start with a $1 or 1 rupee deposit. R equals to 100%. So your money is doubling every year. T or time equals to 1, which is you are looking at a period of 1 year, what's happening in that period. And you keep the number of times compounded, n, a variable. So we want to see what happens if we increase the number of times being compounded. Intuitively speaking, if you increase the number of times being compounded, the amount should increase. So you are getting more interest a multiple amount of times every year, and if you change that number of times you are getting interest, certainly the amount at the end of the year would increase. So this new formula is now 1 plus 1 over n raised to n. Now this is let's call this an. It's a very powerful sequence of numbers is generated from this particular formula. So let's compute a few values of it. If n is equal to 1, the amount is 1 plus 1 over 1 raised to 1, which is just 2. For n equals 2, it is 1 plus 1 over 2 raised to 2, so that's 1.5 square, which is 2.25. For n equals to 3, it's 1 plus 1 over 3 raised to 3, which is approximately 2.37, if I remember correctly. And so on. You can go on forever, of course. Now, people quickly realize that a couple of things are happening with this formula, with this sequence of numbers. Firstly, it's an increasing sequence of numbers. So as you increase n, as you increase the value of n, the value of an increases. The next one, it is a little bit harder to actually compute. It requires, so here is a hint, use binomial theorem and comparison with geometric series. So use these two tools to show that no matter how large you make n, this quantity will always be smaller than 3. Now this is quite an incredible thing because it keeps on increasing. The values of this sequence terms keeps on increasing, but no matter how much it increases, it stays less than 3. A natural next step was to make this upper bound sharper. So people try to compute and find a better upper bound. So can we find a number? So a better upper bound. Can we find a number that is smaller than 3 but it will be larger than all terms of this sequence? So a little investigation revealed that um, the terms of this sequence is less than 2.9, let's say. And then a further investigation revealed that it's actually less than 2.8. Even more investigations reveal that you can make the upper bound better. So 2.72 was an upper bound of the terms of this sequence, and 2.71 was not. In fact, quite incredibly, if you check, n equals to 164 is the first time this particular number makes the leap beyond 2.71. So for n equals to 164, it goes beyond 2.71 for the first time. Anyway, so this is just a fun fact. And people try to make this upper bound sharper and sharper and sharper. And soon they realize that the actual question that they were asking is the following. So let me go to a new board. So they realize that what they actually wanted to know is there a least of all upper bounds, or will they be able to keep on approximating better and better and better? So of course, by computation, we made this approximation better than 3, and from there we did it better than 2.9 and 2.28 and 2.7 and 2 and so on. Can we get a best approximation in some sense? That is there a least of all such upper bounds? So to answer that question, people realize that we actually have to invent new numbers. We need to invent new numbers and declare that number as the least upper bound of this sequence. Because traditional methods are unable to give the least of all upper bounds, because whenever you create an upper bound using traditional approximation methods, you can always get a better upper bound by making n larger. So you have to artificially create, so to say, artificially invent a new number which would by definition act as the least of all such upper bounds. And that number was the Euler number, which is E. Now, this discovery of a new number to so to say fill in the gaps in the real number system was quite revolutionary, because after the discovery of this one, people started thinking about other sequences whose least upper bound needed to be invented. So, and we actually have this axiom needed to be invented. So we came up with this axiom, mathematicians came up with this axiom called the completeness axiom, which says that you have whenever you have a bounded set, that is, you have some upper bound, you will be able to find a least of all such upper bounds. So this is a very crude way of saying the completeness axiom, but that's the essence of it. This, my friends, is the beginning of a fascinating journey into the discovery of new numbers, inventions of new numbers, and in fact, not only new numbers. In the next video, we will show how new functions were invented. And mathematicians could answer a question that plagued them for quite a long time, that is there a function f of x such that rate of change of the function, instantaneous rate of change rather, of the function is same as the function's value. This is an incredible inquiry if you think about it. Today, perhaps most of us know the answer to this question, but when someone first time posed this question, this was quite an incredible thing. That is there a function whose rate of change is actually given by the function's own value? And such a function was invented using the tools of this infinite sequences that we just talked about. Realize that we have actually talked about an infinite sequence here, and we wanted to sort of cap its behavior or cap its moves. And we said that, well, there is a least of all upper caps or upper bounds, and we named it E. So this was a comment about infinity in some sense. And when mathematicians tried to extend this idea, they found new functions by sort of playing with this idea of infinite sequences. And they could successfully answer the question whether there is a function whose rate of change is equivalent to the function's own value. We'll come back to this discussion again. Keep on watching, and link in the description will give you something more interesting. Thank you.